I'm Phil, and today I'm going to look at a design I did 43 years ago, and it was one of the highlights of my career. It was called the ALF machine, and here's the contribution I made, but I'll also include a description of what ALF and ALF is a machine for testing road pavements. So there's a load on a trolley that goes from 4 to 10 tons in 1 ton increments. And the idea is you could have a look at the impact of loading and different masses on a trolley and what damage that could do to a road. So it was designed by the Department of Main Roads in 1982 to 1983, and it was done for the National Association of Australian State Road Authorities. That is, all states contributed, and it was a real Australian team effort. It was going to be operated by the Australian Road Research Board, and they also contributed the data logging system, which I was involved in. The purpose, it was to test roads in a few months, which would normally take about, say, 20 years of loading before you understood what was happening. So being able to accelerate and do all the tests to destroy a road in 3 months meant that you could do a lot of scientific investigation on the behavior of pavements, and you could test your pavement design. The data is going to be more accurate, so there was a lot of scientific instruments, and it was under a controlled environment. And the idea is we could test new materials like the slag from the iron ore furnaces. Could they be used as materials together with other recyclable materials for road construction? So it didn't operate at the same speed as a truck on a road, but it did go at 20 kilometers per hour. And the trolley uh, returned with a wheel clear of the pavement. And that was quite a unique feature of the design. So there were 3 degrees of movement, longitudinal, and that was to put a load on the road or pavement. There was a lateral, and that simulated traffic behavior, and a vertical, which lifted the trolley in the return direction. And I contributed to the electronic control and also with the lateral that is simulating the traffic behavior. So the overall cycle of loading and returning was about 9 seconds, and it could complete 1 million cycles in about 100 days. So this is what ALF looked like on a test site, ready to go and do some testing. So you can see some pavements already marked up, some test strips, and it was moved from one area or one lane to the other. So the history, the design was in 1982. It was operational in Australia from 1983 to 2025. And it undertook 250 experiments over 43 years with 64 million road passes. And it's not only in Australia, it was operated in America and in China. So I helped sell the ALF machine to the US government and to the Chinese government. It was also sold to Saudi Arabia. So this is ALF in China. And this is the brochure we used to sell ALF. The other way of selling it is that we actually built a road at the Sydney Opera House for an international road conference, and we demonstrated ALF at that conference. So the brochure illustrated what ALF was, why it was needed, and how it operates. So how it operates, well, the two rails on the longitudinal direction allowed for a forward loading, so the wheel was in contact with the pavement when it was in the forward direction. And in the return direction, there was a separate set of wheels that lifted the trolley and allowed the energy to return it to its starting position. So you can see the starting position. We're ready to go to the next stage, which was in the forward direction, then the return direction. Okay, so this is what the trolley looked like. And on the top there, you can see the load increments in 1 ton increments. My contribution was the transverse position of the test wheel to give a normal distribution that mimicked traffic behaviour. And I was also interested in the energy conservation of ALF. So this is some of the drawings on what ALF looked like. And you can see that it could be transported anywhere, but you did need a semi-trailer. So it wasn't a small machine. It could be taken anywhere in Australia for testing different road authorities' designs of roads. And here are the specifications. And the additional features, we've mentioned the incrementing the steps of the load. There were no hydraulics used at all, so there were no oil leaks onto the pavement, which could interfere with the accuracy of the results. And there was computer monitoring of the cycles, dynamic wheel load, and wheel location. And this is where I came in. I did that computer monitoring. And there was a slow speed winch for the pavement test, and it was a fail-safe operation. So you could actually go and buy one of these if you had $1 million back in 1983. Okay, so looking at a road profile, a truck here would normally, in a lane, would normally be in the middle of the lane. But sometimes it may venture to the left. And when it did that, it would contribute to the number of passes in that area around about, say, 13% for that left area. In the middle, it's going to be around about 68%. And sometimes it would be on the right, and there's around about 13%. So I had to create a normal distribution control for ALF's lateral movement, and it only moved when it was in the return direction of the trolley. Okay, here are some of my drawings and how I assembled the electrical control system. Everything was mil-spec, so it was pretty rugged, and ALF was used in all weather conditions, and it could easily be transported without damage. In this demonstration, we're looking at the conservation of energy, one of the principles used by ALF. So what we're doing is converting the potential energy, which is got at the moment. It's then converted to kinetic energy, but it's also been given a bit of a push. Otherwise, it wouldn't be able to get back up again. So the ball is demonstrating the way that ALF would currently return and then load. So it's loading the pavement, and while it's loading the pavement, it's getting a bit of a push to the trolley. So what we're going to do is convert the potential energy that we have here, and there's a small electric motor that gives it a little push. So while it's down here, it still has enough energy to complete the cycle. So there's lots of kinetic energy here, enough to get back to its original launch position. So we're going to launch it. The electric motor is just inside. You can hear the motor ticking across. So let's lower the ball, and if this was ALF, our loading position would be here, and the return would be this loop here. So let's give it a demonstration. So that's our second model of the conservation of energy for ALF. In this demonstration, we're going to examine the lateral behaviour of ALF. And this is simulated using a truck with various weights on it. And here I'm using a stepping motor on the bottom that converts the rotary motion to linear motion. So in this lateral behaviour, I'm going to randomly move the truck laterally with a uniform distribution. And the final goal is to use a normal distribution. So it's using a M5 stack stick C computer with a RS485 communications unit, and that's connected to a push 66 module with the stepping motor, and it can then, using the worm drive, provide that linear motion for me. Okay, let's give it a demonstration. So we'll press the button, and we're now getting motion. So it's now seeking a random position laterally, and if it can't move it, so ALF could only move a certain lateral position. If it took too long, it would then crash. So we have to be careful not to exceed the maximum limitation of ALF. And it's telling me on the computer the target. So at the moment we're about 21 centimetres from the midline position. Okay, so we might give that another go. So our new target is going to move 10 centimetres.